then it admits composition. With, let's say, C cups, B minus C sub, or let's write it like this, C sub I cups, B minus C sub I plus 1 hands or saddles, and C sub I plus 2 caps. Okay, so the pieces of the bridge trisection give rise to the pieces of the handle decomposition in the following way. And so the asymmetry here is what's interesting. The fact that you can have unbalanced bridge trisections where the values of the CI are different. So let's look at how that manifests in an example. And then I'll actually prove something using this fact. Okay. So here's just sort of a toy example. Suppose S admits a 5, 1, 2, 4 bridge trisection. Okay. So again, just remember what this means. This means we've isotoped the surface so it intersects the core in 10 points. It intersects the spine in 3 trivial 5-stranded tangles. And in the 3 sectors, we see in the first sector a single patch, in the next sector 2 patches, and in the third sector 4 patches. So it's very asymmetrical. Then S can be understood as the realizing surface in the following 6 ways. Okay, so the first way is so the 6 ways come from sort of the 6 possible permutations of these parameters. Okay, so the first way would be we could have 1 cup. We could have 5 minus 2, which is 3 bands, and we could have 4 caps. And then similar to the second way, now what do I think I just rotate through this? So now we could have 2 cups, thought of this way. 5 minus 4, which is just 1 band, and 1 cap. And then the third and final way is that we could have 4 cups. 5 minus 1 is 4 bands, and finally 2 caps. And then I guess I promised 6 ways. So we can also flip these upside down. So for 4, maybe I'll just write it like this. For 4 through 6, interchange cups and caps. Okay, so this is like turning the Morse function upside down, or the handle decomposition upside down. So if we have a height function giving us a handle decomposition of a manifold, we have handles or critical points of index 0 through n. We can consider the upside down Morse function where all of the handles are sort of transformed into their dual handles. In dimension 2, the dual to a band is a band. So the number of bands doesn't change. This is the picture we've seen a couple times, right? Where the resolving the dual band picture. But the cups and the caps are mentioned. So we really get, this is actually a very useful thing in, say, 4-manifold topology, to take a handle decomposition of a 4-manifold, which maybe you don't understand very well, turn it upside down and get a completely new perspective. So what's pretty cool about this is that trisections give us even more ways of turning our thing around and getting different handle decompositions. So this idea is what we call handle triality. Okay. This is sort of in homage to the duality of of turning a more complex around. Okay, great. Any questions about how this works?
How we do calculate how many bonds we need?
Oh yeah, sorry. It's b minus one of the indices. So this was 5 minus 2, 5 minus 4, and 5 minus 1.
I see.
Yeah, so the cups and the caps, so you pick 2 of these to be the cups and the caps. And the third one, you take b minus it to be the number of bands. And if you just think about that proof, either the proof of how we got a bridge trisection or the one I gave a week or so ago about how to get back to a handle decomposition, you're looking for these dualizing shadows, and those are what give rise to the band. So that ends up being b minus the number of patches in that sector.
I see. So it's how many moves I need in order to go from the 4 connect components to just one.
Oh, well, in this, in this case, that is what it is, right? If I want to go from 1 cup to 4 caps, I actually need 3 bands. But that's not always, see, that's not the case here. If I want to go from 4 cups to 2 caps, I could have as many as 2 bands, but in fact, they were 4. So, I mean, it tells you these are really different perspectives. I mean, and if you just think about the banded link, this is attaching 3 bands to an unknot, whereas this is attaching 4 bands to a 4 component. I mean, it's very different. So maybe I'll just state some exercises for you to play around with this. So first is this sort of interesting question, for which, I guess, triples, C-bar in natural numbers, does a B C-bar bridge trisection exist? Okay. So I almost spoiled this exercise, but not quite with the discussion over here. So that's not too difficult, but I don't want to spoil it even further. Okay. And then, so I guess the exercise here is to draw a crossingless diagram. And draw all 6 corresponding banded link diagrams. Okay. So I've already told you sort of what they'll look like, but here you can actually go through the algorithm I outlined to sort of draw the pictures. And if you draw this thing to be crossingless, then it's not, this is not super difficult. If you want to make it more difficult, you can try to come up with a triplane diagram of the sort that has crossings. I guess I should quickly check that such a thing exists. I must have done that.
Yeah.
Does it? I'm pretty sure. How do we know if a crossingless one exists? Well, this is the simplest perspective, right?
Yeah, I mean,
this band has to be coherent.
Yeah.
So, and this tells us exactly, I mean, perspective 2 tells us what this surface looks like, right? It's a 2-footed.
so that's category of knowledge.
And yeah. Oh, and it is actually also a factor. This will be unknown, which will come up in a second. Yeah. Okay. Great. That's good enough. Okay. So let's see if we can prove even more things. So suppose S admits a. So from this perspective, one of the simplest types of bridge trisections we might consider are those where one of the patches has the same, one of the patch systems has the same number of patches as bridges. Okay. Okay. So then what this tells us is that S has a handle decomposition with, and so now what I'm going to do is I'm going to choose the bands to come from that first parameter. So I'm going to have C2 cups, C3 caps, and B minus B equals 0 bands. Okay, so this is a nice type of surface where we have no bands. So we immediately see a couple of things. The first is that we have to have C2 equals C3 equal, we'll call it C, because if we start with some number of cups, we attach no bands, then we need to cap off with the same number. And what we also see is that S is the split union of C copies of the unknotted tube sphere. This follows from the fact that this goes back to the fact that trivial disk tangles are unique up to boundary. So we're attaching one as the cups and one as the caps, and there actually ends up being a double. And the third thing you see is that the first two tangles have to be the same. And by this I mean in a diagram, I guess. Maybe what I really mean is the tangle diagrams are the same. Maybe I mean diffeomorphic row boundary or something like that. So we can assume the first one looks like that. The second one also has to look like that. And the reason is because the union of these two is a B bridge splitting of the B component unlink. And so that's as nice as it can be. And then over here, we have a priori something interesting going on. But the fourth fact is that, let's say like this, the bridge trisection is standard. And I realized that I think I defined standard, but I don't think I defined it in the way I wanted to define it. But what I mean here, I'll just say, is that actually, even though this has crossings a priori, we can actually undo the crossings. Okay? And that's because, green and blue together is a C component unlink, and we talked about how we can undo this bridge splitting of the C component unlink, but that will change blue, and red is the same as blue, so we can do it without. Normally we could do that, we could undo the crossings here by pushing the complexity into red, but because red and blue are the same, red gains no complexity. So this guy ends up with no crossings. So this third tangle, it ends up being maybe a little bit complicated based on the number of components, right? We have to have, this tangle is going to be a little funky depending on how many components we have. So this handle triality gives us already a nice little result, which is that if one of the patch systems is maximally sized, the surface is automatically very simple, and the bridge trisection itself is as simple. Okay. Okay, so now I'll state two theorems that were sort of alluded to before, that are classical theorems from low-dimensional topology. So the first is the theorem of Charlemagne. From 1985. I think this theorem also has incarnations in work with Abby Thompson, and then maybe even in a paper is the split union of two knots so it's a two-component link. And B is a band for L such that L result is unknotted. Then L is an unlink. And B is a connected sound band. Okay, so essentially the picture is this. So this is a really strong result that says if we attach a band to a two-component split link and the result is an unknot, then our original knots had to be unknotted, and the band has to be as simple as yeah.
The statement of the band has to be simple. Is that actually any content? I mean, if you have split link and a band going from one to the other,
Actually, I
how
think
does
that's
it get complicated? What's an
um,
example of a complicated band from an unlinked to an unlinked? I mean, one.
well, yeah, that's the main content. I mean, if I had stated this where this was just an unlink, that would already be a major theorem. That's right. The content about the band is essentially two theorems.
What's an example of a? I mean,
Well,
of
there's
a
none in this
complicated
case.
band? Where I mean,
Okay, let me make a comment here. So I'll come back over here. I purposefully saved this little piece of board here. So in particular, a two knot in sorry, the Charlemagne's result. A two knot S4 with two minima and one maximum is unknotted. Not a question. Question. What about C greater than or equal to 3 minima and 1 maximum? So this is exactly the question. It's actually very tricky. Even one of the unlinks, well, so in a sense, the question of attaching bands to an unlink and getting an unlink is all knotted surfaces. So
right, but if I have what I'm trying to say is if I have a split unlink, split link, and I have a band from one component to the other, can I not make that standard by making this component really, really small and untying it? In order to do that, you need a sphere. You need one of your splitting spheres to intersect the band in a single. To intersect the band once. That's right. It can go through that one. That's what.
Yeah. So this
I can't
band
pull it
really intersects.
That's right. Okay. I needed that basic. Yeah, I forgot. The point is the band can link the other.
Yeah.
Thing. Right.
Yeah, and I'm not super familiar with the proof of this, but I would imagine that it's one of these thin position arguments where you're exactly trying to minimize these intersections.
Yeah.
With these splitting spheres.
So that's an open question?
Yeah, this is a big open question. So we make our ghost bigger. And is every two knot with 3 minima and 1 max unknotted?
There are no counterexamples for any C bigger than 3.
There are no known counterexamples. Conjecturally, in fact, having a single maximum is enough, as we'll see. That follows from. Okay, then we have a similar result from Bleiler and Charlemagne a couple of years later, which says or an unknot, an unknot I'll call K, and K resolved along the band is an unknot. Then the right way to say this is there's a spanning disk for K such that the disk union of the band is an unknotted Mobius band. Then there's a spanning disk D for K such that D union D is an unknotted Mobius band. And by an unknotted Mobius band, I mean the core of the Mobius band is unknotted. So, I mean, essentially what I'm saying is we have K, we have D, and the band is just this. So it's a similar result when there's only one component. By the way, these are sort of analogs of famous theorems from Dane surgery, right? So this can be thought of as having a Dane surgery going from S3 to S3. And this can be thought of as having a Dane surgery going from S3 to S1 plus S2. Although these don't imply, they're not logically cool. So let's use this to prove something about bridge dissections. Okay. Now we'll suppose, so this will let us do one better than our last one. Suppose S admits a B minus 1, C2, C3 bridge trisection. Okay. So among all of the handle decompositions this might admit, it has one with a single band. And S admits a handle decomposition with C2 cups, B minus 1 equal 1 bands, and C3 caps. So the key thing here is one band. These theorems give us some indication that maybe we could just understand the case when we're only attaching a single band. Okay, one thing that we immediately see from this is that the C2 or C3 has to be C2 or C2 plus or minus 1, because attaching a band can only change the number of components in your link by the most one. And so we have the following proposition, which says that, well, I kind of skipped ahead. What I should have stated is the following corollary to the Charlemagne and Weiler-Charlemagne result, which is that if B is a band for L such that L resolved around B is an then B is a connected sum band or a trivial twisted band. Okay, so this is a stronger result than what was proved over here, but I think that it follows in a fairly straightforward manner from these results. I guess I can try to sketch the proof. I don't think I've heard that.
Could you maybe try to say why this Weiler-Charlemagne theorem is hard?
Well, a priori, you could just attach a very complicated band to an unknot and get an unknot.
It's got to be a, combinatorial thing when we in the sense of, like have a twist in it because it's got to produce one component afterwards. But
Yeah.
it could be not a,
Or maybe you could even have more
Oh,
twisting.
the core circle could be a non-trivial knot.
Yeah, exactly.
yeah.
Oh, okay.
Yeah, I mean, it's very believable. I don't think anyone would have ever thought that it was not true. It's more just a question of getting the sophisticated enough three-manifold technology to actually
Yeah, I just didn't know what you meant by that. Like, is it in 4 dimensions or 3 dimensions?
Yeah, these are
The
three-dimensional
core
groups.
circle is.
Oh, yeah, the core, oh, sorry, yeah, that is confusing. An unknotted Mobius scheme. Yeah, that's very confusing. So by this, I mean unknotted in S3. So the core of the band, the core of the band is actually unknotted. Okay, so I think I'll table the proof of this because I didn't bring those notes and I don't want to mess it up. But the idea is that even if there were more components here, we can essentially use the fact that we have an unlinked before and after. And so the proof basically goes, take a collection of spanning disks for L resolved along B and promote that back to the collection. So sort of all the action is happening here. And maybe you think the band hits all these other guys, but actually you can straighten it out. Oh, wait. So then the corollary that we get based on this is that these types of bridge trisections are completely trivial, totally standard. So B minus 1, C2, C3 bridge trisections are standard. And again, what I mean by standard is I essentially mean like a split union of maybe stabilized bridge trisections for simple surfaces. So in this case, the surface that we get in this case is it's either the disjoint union of no matter which C you want to do. Yeah, so let's assume without loss of generality, since we could flip this thing upside down, let's assume that this is lower so that it matches that picture. And then, so this is either the disjoint union of C2 unknotted 2 spheres in this case, or it's the disjoint union of what did I C2? C2 minus 1 2 spheres, disjoint union of projective plane, not a projective plane. Very cool. So I'm hoping over the next couple of lectures to kind of put a bow on bridge trisections and then move on to talking about 3 manifolds and 4 manifolds. So with that in mind, I think I wrote this in the notes that I'll post in the Dropbox if you want to look at it. All right, any questions? So maybe I'll just put a bow on this. So there's this notion of handle triality that I think philosophically is really interesting in the trisection case. The fact that you can have these different perspectives on your manifold. And these sorts of results are evidence that you can actually use it to prove things. So maybe that's all I'll say about that for now. Any questions about this stuff?
So is there a sense in which you can, are there some handle decompositions that aren't, triadic in the sense that they don't, by some simple combinatorial, have a handle triality, and therefore they couldn't come from a trisection?
I don't think so, because I think by changing B, so that's sort of the converse to that exercise. But I'm kind of guessing. So, yeah, because I mean, you just do this. You just take the number of cups and the number of caps. That's C1 and C3, and then you change B to get the right number of bands. That won't. You have to take the cups and the caps probably to be like not the larger of the.
Yeah, makes sense. I mean, if I have like X1 handles Y two handles and
Oh, you're
X zero
for-
handles, sorry, X zero handles, Y one handles, and Z two handles. Y bridges, or whatever you call them, fans.
Yeah,
Is there a?
yeah, I mean, I think
Does
it's,
there exist B, C1, C2, C1, I2? Yeah, okay.
okay, now we just need to make sure these are positive natural
Well,
numbers.
yeah, I need to know that the Euler characteristic there is the Euler characteristic there, which will be.
That will be automatic. We need these to be positive natural,
I
they need to
see,
be natural
I see,
numbers.
I see. Yeah.
And so in particular, you need B bigger than Y, right?
Where did B come from?
I made it up.
But it'll always be, you'll still get the right Euler characteristic.
Actually, any B would
Yeah,
work,
that's
right?
Yeah, yeah. You just
Any
make
B,
large enough
yeah,
B,
any
yeah.
B bigger than Y.
Right, I see. Yeah. Okay.
Yeah, so the converse is a little bit more interesting. There are actually some triples of this form that
Yeah.
don't count. Good question. Okay. So the next thing I wanted to talk briefly about is the fundamental group of, I guess, of surface link complements. And I guess, Jason, you talked a little bit about this last week?
Yep.
Hopefully I won't say anything too redundant. I won't say a lot that's redundant because I'm not going to say a lot. So there you have it. All right. So let's just start off with an observational lemma, which is that let's let D in, say, Z be a trivial C-disk tangle with the boundary of this thing given by YL. So this matches our notation. Then the map, the inclusion map, or the map I star from pi1 of S3 minus L to pi1, sorry, Y minus L, Z minus E, induced from inclusion is an isomorphism. Did you talk about how to like get relations from bands and stuff?
I guess not.
Okay.
No.
So why is this true? Well, what's the right way to think about this? I mean, you can think about it, probably the best way to think about this is a trivial disk system can also be thought of as each component is a cone on the boundary. So this guy is an unlink, right? So YL, so here's like I don't know if this is a proof, maybe this is a proof. This is an unlink, and ZD is cones on the unlink. Right? It's not the cone because the cone on the unlink would have a single cone, but it's just a collection of cones. Another way to think of this is, remember a trivial disk tangle, we could think of as a trivial tangle cross I. And that thing has free group, and so that's just going to be crossed I, so that should give them. So this is a free group, so these are both, they're both free on C letters. And there's a natural isomorphism. Oh, okay. Oh, I said that. Oh, okay. So the corollary to this is that, two corollaries. If S admits handle decomposition with, let's let's say C1 cups, N bands, and C3 caps. Right? Then pi1 of the exterior of the surface as a presentation with C1 generators and N relations. Or of course, by duality, C3 generators and N relations. And the idea here is just, we've got this C1 component unlinked, and as we go up in time, nothing interesting happens. Maybe it wiggles around as we go up in time. And then what we do is we attach a bunch of bands. And each of these bands is going to give us a relation. And the relation it's going to give us is that, let's say that this meridian here is going to get identified with. I won't say any more about this, but each band, when you're coming up on that saddle, you've got these two pieces that are getting closer and closer together. These are each carrying some element of fundamental group as a meridional element. And when you get here, they become the same element. So that gives you a relation. Okay. So another corollary is that if S is a BC rich trisection, so with spine, so let's just recall the notation for the spine, the union of these three balls, these three tangles. So the result here is that the fundamental group of the surface link exterior is actually isomorphic to the exterior of the tangle, the three tangles in the spine. So let's write that. So then 1 of S4 minus S is isomorphic to pi1 of the union of these balls minus the union of the tangles. Okay, and this is because how do we get to the surface from the spine? We just add on these trivial disk systems, these trivial disk tangles, but because of this isomorphism, that's not going to add any relations or anything to our group. Okay. In particular, pi1 of S4 minus S has a presentation with so there's a couple of different presentations. Let's see where each of these come from. The first is we could have 2B generators and 3B. So where's this? Okay. From thinking about the group of this spine, spine exterior. Right? We start with our 2B punctured sphere. So I guess maybe that's supposed to be 2B minus 1. Well, no, let's just go ahead and give a generator for each puncture on the sphere. And each of the tangles go up and come back down and identify two of them. So we get a relation for each strand of each tangle. That gives us 3 relations. Okay, but of course this is overkill. So so what we can do is we can assume one of the tangles is, say, as simple as possible. So it just pairs the ith generator with the I plus first generator for odd I, say. And in that case, we can get rid of half the generators, and we're left only with the relations coming from the other two tangles. And then we can actually do even better. This is the most interesting case. We can actually assume that we have CI generators and B minus CI plus or minus 1 relations. for any I and Z. And the way this works is we actually, you can think about, say, in your triplane diagram, you standardize the first two tangles. So it's just a very simple unlike. So maybe I should draw such a simple picture. All right, so maybe you standardize your first guys so that you get this. Some bridge splitting of an unlink. And then where are your generators going to come from? Well, instead of getting a generator from each of these bridges, we're actually just going to get one from each component. Okay, from this unlink exterior, where you have a free group on 4 generators. And then these relations come from the bands. I see. So one way to think of this is actually going back to that proposition about how to extract a handled decomposition from a bridge trisection, where you get this many cups and this many bands. So, and actually then, okay, so, and one remark is that these presentations are meridional. They're meridional, right? So what that means is that there's a curve in the surface link exterior. So this is a little bit difficult to draw, but this is our surface link in S4 drawn down a dimension. And we have a regular neighborhood of it, which locally looks like a D2 neighborhood. And so a meridional curve is any curve that's isotopic to a disk intersecting the surface in a single point. And so this says that these generators can be chosen to be meridional. And of course, the way we were choosing them is that they're actually the little meridians of the bridge points. Okay. All right, and so I guess, have I defined like the bridge number of a surface link? I didn't minimize. Okay, let's do that. Who knows how many little loose strands there are that just fall on the way. So we still haven't talked about stabilization, destabilization, and uniqueness. I'm definitely going to do that. We haven't talked about shadow diagrams. Definitely going to do that. I'm speeding through fundamental group concerns right now. If there's anything you think that I'm maybe not mentioning, let me know. All right. Okay, definition. I guess this is the bridge number. Bridge number, B of S of a surface link S is the smallest value B such that S admits a B bridge trisection. There's no reference to the C's. It's the I's. I mean, you could probably also define something called the patch number. Patch number, yes, is the smallest value, let's say, C, or say C, such that S admits a B C bar bridge trisection C for some I. Okay, so number of patches you can find in one sector of a bridge. Okay, so the corollary that we have from all this stuff over here is that C of S is bounded below by the meridional rank of pi 1 of S4 minus S. Okay, I guess that's the point. So, and meridional rank, I think, I define good. Does that make sense? So, by the way, as far as we know, the bridge number and the patch number are essentially the same thing. So I guess let's make this a remark. I mean, I'm not saying they should be the same thing. I'm saying that we don't know any examples where they're actually different in an interesting way. So the remark would be that if a minimal bridge trisection for S is balanced, it's a BC bridge trisection, then B of S and C of S are related by the Euler. Okay. Now, what could be a little bit more interesting, I think, is when maybe you can lower some of the C's and like you can lower B, but only by lowering. I guess that still would be. Oh, maybe at the cost of, yeah, so maybe, well, anyway. Something funny happens here when it's unbalanced, and we don't really know anything about that. All right. So I think the last thing I want to say here, and then next time we'll talk about the unknotting conjecture. Okay, the last thing I want to say here is the following. Maybe don't make this a 0, why not? For each C greater than or equal to 2, there exist infinitely many 2 knots, distinct 2 knots, with patch number C and bridge number 3 and bridge number 3C minus 2. So for example, these are 4, 2, 7, 3. Okay, so in particular, we had talked about how if B is less than or equal to 3, the surfaces are unknotted, right? That was one of the results we talked about. We had a classification of low bridge number surfaces, B is 3. Well, once you get to B equals 4, you start getting infinitely many different 2 knots. Okay, so 1 minute left, so I'll just tell you the bones of the sketch. And so this is to show that meridional rank is preserved under spinning or yeah, I think that's this is under spinning. So, you know, we talked about how like 2 bridge knots all have meridional rank 2. Or so more importantly, torus knots have meridional rank Q. And that value increases. So what you want to then claim is that the spin of a torus knot, or the spin of a 2 bridge knot, has the same meridional rank as the original. That's what I mean by that. And so let's see. What's the second part of this? Oh, yeah. Show that if not K in S3 admits a B bridge splitting, or let's call it C bridge splitting, then the spin of K admits a 3C minus 2, did I don't know if I got it. 3C minus 2C bridge trisection. Okay, so those are the two steps for the proof. And this is written up fairly clearly in the paper with Alex, if you want to look for the details there. Okay, so next time we'll talk about a knotting conjecture, which has to do with when surface links have the simplest possible fundamental group. And we'll talk about questions? That didn't overlap much with what you were saying, did it?
No.
Okay. Also, whatever Jason said, you know that too.
That thing over there, if it is unbalanced, then the sum of all three of the C's is basically the bridge, is this related to the bridge
Yeah,
number.